Okay, so picking up where we left off with limits, this is section 1.2 and 1.6. Going a little bit out of order in the book just because we're focusing on just evaluating limits today. And the stuff that we do in section 1.6 is really a pretty simple follow through of what we're going to do in 1.2. So even though we're going out of order in the book, it's not like anything's going to be that much more challenging in 1.6 than it is in 1.2. So we're focused today on computing limits. And before we get too far into this, just a reminder, like I mentioned last time, the idea of a limit is something that's going to be super, super important to us. So as we go through these problems, try to not just get an answer and feel like, okay, I know how to get an answer. That's all I need to know. The important part about this is understanding conceptually what's going on. That should always be your primary focus, especially earlier on in the year when we're doing these easier topics. Try to focus on the conceptual or the big picture and be less concerned with, okay, I know how to solve this particular problem. So as we go through this, you'll see I'll refer to things graphically sometimes, but try to keep in your mind, what is this answer actually telling me as we go through these? So to start with here, we've got some, first of all, just basic ideas that I want to make sure everybody's clear about. So the first part of this is to talk a little bit about just some really basic limits that everybody should know. And the first one here, if we take the limit of a constant function, we're going to get a constant value. That's what this one is showing. So if I had, y is equal to k, where k is, let's say y is equal to 4, regardless of where I evaluate the limit, I'm always going to get the same value. Second one, if I have the function y is equal to x or f of x is equal to x, then whatever the x value is, the y value is going to be the same. We know that's a continuous function, so the limit value is going to equal the function value. And then the idea here of the one-sided limits, we talked about this a little bit last time. First of all, with the notation, the minus on the 0 meaning the limit as we approach from the left, the plus on the 0 meaning the limit as we approach from the right. And then the negative infinity and the infinity are indicating that that function is tending towards negative infinity or positive infinity as we approach 0 from the left or from the right. Okay, so let's take a look at some properties. These are basic properties that we're going to use for limits, but like I said last time, since limits are going to apply to everything we do this year, you're going to see these same properties used over and over and over again. So even though they're basic, keep in mind, these are going to be the same limits we're going to use for derivatives. They're going to be the same limits that we're going to use when we're dealing with integrals, and they're going to be the same limits we're going to use when we're going to be dealing with series. So even though the application will change, since we're all rooted in limits, these are very, very basic ideas that are going to carry through the entire course. So most of these are self-explanatory, and they're things that really, for the most part, are things you would figure out without even having to stop and have a property actually tell you. But this is just the mathematical justification for why these things are true, so that when you use them, it's because these theorems are stating that these are things that are true. So the first thing is we have two functions here, f of x and g of x. And for both of them, if we take the limit as x approaches a, the limit exists. For f of x, we get a limit of L1. For g of x, we get a limit of L2. And you can see for property A, if we took the sum of those two functions and we took the limit, that's the same as taking the limit of each one of those functions individually and adding the two limits together. So essentially, you can take the limit of a function that has multiple components to it or multiple terms. You can take the limit of each term independently. Same thing applies when we're looking at the difference of terms. You can see on B, if I've got the difference of terms, I can take the limit of each term independently. When we get to C, we've got the product of two functions. So this is a little more useful. Now, if I have a limit where the function looks, a little bit difficult to deal with, I can break this apart. If I can take the limit of the two parts of the function that would multiply to make the original function, then I can find the limit of each piece independently and multiply their results. That gives me the limit of the original function. Same thing if I've got a quotient or a rational function, I can take the limit of the numerator and the limit of the denominator separately, provided that the limit of the denominator is not 0. And also if I have some sort of a root function. Typically for us, we're going to deal with square roots and cube roots, but you could see any root here. And I can take the limit of what's inside the root, or take the limit of the radicand, and then I can apply the nth root to the result, and that would be what the limit would be equal to. So like I said, keep those in mind. Those are things that are, things that kind of go without saying, and they're things that you would, they're kind of intuitive. You would figure them out anyway, but we do need to state them so that we can actually use them. Okay, so let's take a look at really our primary focus in this section is just evaluating limits. And we talked a little bit about this last time, so I'm not going to spend a ton of time on this. But this first one, we have the limit as x approaches 1 of x minus 1 over x squared minus 1. So what I want you to do is just take a second, pause the video, and solve that. Now, what I'm hoping as you practice with these, what I'm hoping is you get to the point where you can do some of these easier problems in your head. This is one where if you plug 1 in, you can see that we're going to get 0 over 0. So we've got an indeterminate form. But from what we talked about last time, hopefully you remember that we can just factor this. And what I'm really expecting you to do is get to the point where you do this in your head and you don't show me any steps. I'm going to assume that you know how to solve this. So in my head, what I would be doing on this one is I'd be saying, okay, in the denominator, I have x minus 1 times x plus 1. And then the x minus 1s from the numerator and the denominator, those are going to cancel out. And I'm going to have 1 over x plus 1, which then is going to simplify to 1/2. So we want to get to the point in this class where we're skipping a lot of those basic steps, because when we get to the end of the year, we're going to be doing problems that have 10 to 20 steps. And if we're writing down every little thing that we do, it's going to take way too long to write out a problem. And we don't need to write out things that are, for somebody in a more advanced mathematics class such as this, we don't want to write things out that are obvious to somebody who's reading the work. Okay, so if you look over on the right here, we've got this g of x function defined. So essentially what this is doing is the original function that we took the limit of on that problem on the left, the g of x function is a rewriting of that function where we have now defined a function that is continuous through the point where x is equal to 1. So what we've done is we've taken a function that had a hole in it, x minus 1 over x squared minus 1. There was a hole at x is equal to 1, or a removable discontinuity at x is equal to 1. By defining the function value to be 1/2 at x is equal to 1, we've now taken that hole in the graph and we've filled in that hole in the graph. So I want to point that out because you might see some problems on your assignment. You might see problems on your quiz or your test where it says rewrite this function so that it's a continuous function. When you have a removable discontinuity in your domain, all you're doing is you're finding the limit at that point so that you can make the function value equal to the limit value, which then makes it continuous. Okay, so here are some more problems where I just want to briefly talk about how you would solve these. So algebraically, we talked about factoring last time, and we talked about expanding things out when we have algebraic expressions. Well, on this one, you may or may not have seen problems like this before. We have a square root within a rational function. And so when I plug 0 into this, I'm going to see that I get 0 over 0, which is an indeterminate form. Whenever you see those indeterminate forms showing up within your limit, the first thing you should be thinking of is, okay, I need to do some sort of algebraic manipulation. Usually I think about factoring first, and then I think about some sort of an expansion. And if that doesn't work, then I start moving on to other things. Well, this is sort of a special case. What we can do in a case like this is we can multiply by the conjugate expression. So I'm going to multiply by the conjugate of the numerator to both the numerator and the denominator. And the reason I can do this is because essentially what I'm doing is I'm multiplying by 1. I'm multiplying by square root of t squared plus 9 plus 3 over square root of t squared plus 9 plus 3. If I divide that out, that's 1. So really what I'm doing is I'm taking this function and I'm rewriting it in alternate form so that I have hopefully something that will show up that will allow me to solve the limit. So when I go ahead and multiply that out, what I'm going to end up with in my numerator is t squared plus 9 minus 9 over t squared times the square root of t squared plus 9 plus 3. And at first glance, this kind of looks like a mess. Doesn't look like I've done myself a lot of good. But what you'll see pretty quickly here, the 9 and the negative 9 are going to add up to make 0, which then leaves me this limit with just t squared in the numerator. So what I can do with that t squared, this is essentially t squared over t squared times all of this stuff. I can cancel out the t squareds. And now what I have is the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. And so essentially what I've done, just like we did on the factoring problem a minute ago, is I've removed the discontinuity. So at t equals 0, I had an issue. Well, now the t's canceled out, or the t squared's canceled out. So now I no longer have that issue. Now I can just do direct substitution. And when I directly substitute into this, I'm going to get 1 over the square root of 9 plus 3. That's 1 over 3 plus 3, or 1 over 6. Okay, so not really anything that's too difficult, but it's sort of a special case. Like I said, when you see these square roots, a lot of times you're going to want to be thinking about multiplying by the conjugate. This next one, we're going to spend some time on this at the end of the lesson today, but this is actually a special case. You could look at this graphically on your calculator if you want. And if you want to pause the video and graph this on your calculator, you can do that. But I will tell you, this one is going to turn out to be 1. This is one that you need to memorize. And you'll see why later on, why this is a limit that you're going to want to memorize. We do have a way to prove this, but it's kind of a long drawn out process. And we use this limit often enough that that's one that you just want to know. I'm not going to tell you to memorize a lot of things in this class, but the things I do tell you to memorize are going to be things that you don't want to work out by hand, or there's not an easy way to come up with a solution without just knowing it. Okay, so this one, we've got the limit as x approaches 0 of pi over x. Now, what I want you to be thinking about in a lot of cases is I want you to be thinking about transformations. So think about this for a second and think about, okay, pi over x, what graph do I know that this is a transformation of? And then in addition to that, what type of a transformation is that? Okay, so hopefully you're thinking about the 1 over x graph. And the 1 over x graph is one that really you should know. And if you don't, I promise you, you will know it very, very quickly because we're going to use it all the time. But even if you didn't know it, using what you know about graphing rational functions, you could easily come up with this graph and see that behavior. And you can see at x equals 0, we've got a vertical asymptote. We've got from the right side, we're approaching infinity. From the left side, we're approaching negative infinity. So this limit fails to exist or does not exist. All right, so another problem here, just for a little bit of practice. We've got the limit as x approaches 0 of x cubed plus the cosine of 5x over 10,000. Now, remember those properties we looked at a minute ago. One of the properties was I can take the limit of these individual terms one at a time and then add up the result. And whatever I get is going to be the result of my limit. So in this case, I can take the limit of x cubed. If I find the cosine of 0, the cosine of 0 is 1. So when I evaluate this, essentially what I'm looking at is limit as x approaches 0 of x cubed would be 0. Cosine of 0 is 1. So I get 1 over 10,000. And this whole thing would just be 1 over 10,000. And just like I mentioned earlier, you really don't need to write the 0 plus 1 over 10,000. You could just go straight to the solution on a problem that's simple like this. But keep in mind, the first thing we always want to try is direct substitution. Don't assume because the function looks complicated that the easiest method is not going to work. Always do direct substitution first, and then from there you can kind of go on to your other methods. All right, so we looked at this graph last time, 1 over x squared, and we talked about the fact that this limit was equal to infinity. I want to be really clear on the whole idea of something being equal to infinity. You can't really be equal to infinity. Like it says here, infinity is not a number. So really the most mathematically correct way of writing this limit would be the limit of the limit as x approaches 0 of 1 over x squared is approaching an infinitely large value. That's the most mathematically correct way of writing this. Now, it used to be that this is the way we wrote all limits. We used to write limits with an arrow like this because it makes it a little bit more obvious that this is saying that this function is approaching an infinitely large value. Over the last, 20 to 40 years, that notation has really been phased out. And where it hurts with understanding is in situations like this, because what your textbook will say and what a lot of resources will say these days is that the limit as x approaches 0 of 1 over x squared is equal to infinity. Well, it's not technically equal to infinity. So keep that in mind. It's not wrong to write it that way because it's generally accepted nowadays that it's equal to infinity is an okay way to write it. But keep in mind what it actually means. It doesn't mean it's equal to infinity. It means that it's approaching an infinitely large value. So technically, infinity is not a number. So technically, this limit doesn't exist. So we're still going to write that it approaches infinity or that it's equal to infinity because that allows us to describe the behavior. We do have a behavior that will help us understand what's happening with the function, but technically this fails to exist. So technically this fails to exist. So keep that in mind when you look at something like that. Keep in mind what that means. Like I said, the notation is a little bit misleading. If you want to use the arrow like I did here, saying it's tending towards infinity, that's fine. If you want to write the equal to, that's fine as well. It doesn't really make a difference. Like I said, you're going to see it written both ways. I just want to make sure you understand what it actually means. We looked at this limit last time graphically. The limit as x approaches infinity of 3x squared plus 4x plus 5 over the square root of 16x to the fourth minus 81. So last time I said graph it on your calculator, figure out what it's approaching. This is essentially a horizontal asymptote. Well, there is a way to solve a problem like this algebraically. And this isn't really in this section, but since we're talking about a lot of algebraic processes to solve limits, I wanted to put this in here because this is sort of solving it algebraically. We're going to algebraically manipulate this thing so that we can solve individual limits. So right now, if I were to look at this, I took the limit of the numerator. So think about the property that we had at the beginning. We had the property when we had a function that had a quotient or a rational function. So if I took the limit of the numerator, I would get infinity. If I took the limit of the denominator, I would also get infinity. So infinity over infinity is another of what we call the indeterminate forms. So we've talked about 0 over 0 a lot. This one's infinity over infinity. So from that method, direct substitution doesn't really give me a solution. So we saw how we could solve this graphically. But what we can also do is we can go through and we can think about how can we rewrite this in a way that's going to allow me to solve this. So we're going to do something where we're essentially going to multiply by 1 again. And what I'm going to do is I'm going to take the highest degree term in this entire function and I'm going to divide everything by that. So essentially, I'm going to multiply everything in the numerator by 1 over x squared. I'm going to multiply everything in the denominator by 1 over x squared. And what that's going to create in the numerator, I would get 3x squared over x squared plus 4x over x squared plus 5 over x squared. Okay, so you can see how I've multiplied by 1 over x squared to all the terms. It's a little trickier in the denominator because when I multiply by 1 over x squared, well, if I move that into the square root, that's essentially multiplying by 1 over x to the fourth. So I would have 16x to the fourth over x to the fourth minus 81 over x to the fourth. So now we're still using these properties to solve this limit out now that we've gotten to this point. Remember, I can take the limit of all of these terms individually. I can take the limit of the numerator and divide it by the limit of the denominator. So a lot of the properties get thrown together into a single problem like this. Now you notice that the x squared cancels out. That limit clearly is just going to be 3. For this one, we're going to get 4x over x. And when I evaluate that, when I take the limit as x approaches infinity, that means the denominator is going to get very large. This is going to approach 0. I'm going to circle the 3 here so we remember we had that 3. 5 over x squared, when I evaluate that limit's also going to approach 0 because the denominator is growing in value, the numerator is not changing. In the denominator here, you can see that we've got this 16x to the 4th. And then when we look at the 81 over x to the 4th, that's going to approach 0. So now in the end, you may remember that we got 3/4 on this problem before. Well, we've got 3 in the numerator. In the denominator, we've got the square root of 16, which is 4. So same result as what we got graphically, except now we have a way to algebraically show what that solution actually is. Okay, so the second section that we're going through today, for the most part, when we look at the limits of trig functions, when we look at sine and cosine and tangent, for the most part, when we evaluate those limits at points that are within the domain of those functions, it's going to be exactly the same thing. If I take the limit of sine anywhere, I've got a continuous function. Whatever sine is equal to at that point, that's the limit. Same thing with cosine. Where we start to run into some issues is when we have vertical asymptotes. Then we've got to be careful with the behavior around those asymptotes. And we talked about the one-sided limits and dealing with that. What I really want to focus on in this section are the special cases that you might see. So we had this problem that I told you earlier you need to memorize. The limit as x approaches 0 of sine x over x is equal to 1. We're going to prove that here in just a minute. I'm going to show you how that works. But before we can do that, we have to learn something called the squeeze theorem. So the squeeze theorem is a way for me to deal with a function that I can't really evaluate for whatever reason at some point. And so what I'm going to do is what we call bound the function. I'm going to take some function here. We're going to say f of x is the function that we really want to work with. Well, for some reason, f of x is hard to evaluate, maybe at a point, or maybe it's just a hard function to work with. So I'm going to find a function that's always greater than or equal to the f of x function. I'm going to find a function that's always smaller than that function. So I've sort of got an upper bound and a lower bound. And if you look at this diagram down here, you can see f of x, that's the function we want to work with. It's the one in the middle. H of x is the higher function. G of x is the lower function. So we've got it bounded. F of x is bounded between h of x and g of x. But notice what's happening at the point C. At the point C, it looks like all 3 of those are equal. And so if we are able to bound our function like that, you can see that if the 2 outside limits, and when I say outside limits, I'm talking about these functions that are on the outside of this expression. If those 2 functions approach the same value at some point, then in order for that original compound inequality to be true, in order for g of x to be less than or equal to f of x to be less than or equal to h of x, in order for that to be true, the 2 outside limits are equal. The inside limit has to be equal to the same thing. And that's what the squeeze theorem says down here. If those 2 are equal, then the one in the middle has to be equal to the same thing. Okay, so we are going to use that now in an easy way first, and then I'm going to show you how to use that for sine x over x. Okay, so we've got another type of limit here. It says the limit as x approaches 0 of x squared sine 1 over x is equal to 0. Okay, so again, think about what we're actually trying to do. We're not just trying to get a numerical result. We're trying to think about what does this actually mean? Okay, so we're trying to figure out what's the behavior of this function at 0. Well, think about if you plug 0 into x squared, you would get 0, and then we have the sine of 1 over 0. So we have an undefined value. Well, how do we take the sine of an undefined value? We can't do that. So that means we've got to find a different way to evaluate this. We don't know what the behavior of this function is at 0. Okay, so to use the squeeze theorem, it says to prove this. And to prove this, we're not going to write like a formal mathematical proof, but we do have sort of a process that we need to follow. So the first thing I need to do is I need to start with some statement that's going to justify what my thought process is. And I want to start with a statement that I know to be true. So in this case, sine of 1 over x. Well, I don't know a lot about what's happening with sine of 1 over x at 0, but I do know the biggest that sine can ever be is 1, and the smallest sine can ever be is -1. So I started with a statement that I know to be true. And now that doesn't look exactly like the function that I have, because my function was x squared sine 1 over x. Well, now let's manipulate this so it looks like my function. I'm going to multiply everything in this inequality by x squared. So that's going to give me -x squared being less than or equal to x squared sine 1 over x. And that's going to be less than or equal to 1 over x squared. Okay, so now I've got, less than or equal to x squared. Okay, so now I've got my function bounded like I wanted. And I never would have known that x squared sine 1 over x could be bounded between x squared and -x squared unless maybe I played around with that on the calculator and looked at the graph. But now I know this is true. Okay, so let's take a look at what the squeeze theorem said is, if the limits of the outside parts of this inequality are equal, then the limit of the inside part has to be the same. Well, the limit as x approaches 0 of -x squared, what would that be? Well, that would be 0, right? Because -0 squared is just 0. And I know the limit as x approaches 0 of x squared is also 0. So those two things are true. So since those are true, I can say therefore, and remember those 3 dots sort of in a triangular configuration, that means therefore. So therefore, the limit as x approaches 0 of x squared sine 1 over x, well, remember the squeeze theorem said if the outside parts are equal, then if those two are the same, then the limit of the inside part has to be the same. This one's also going to have to be 0. So even though algebraically I couldn't solve this, the squeeze theorem sort of gives me a workaround so I don't have to work with it algebraically. This would be one that, maybe I could graph it on a calculator, but you could never graph that out by hand, not very accurately. So now I've got a way to solve it out. So the squeeze theorem has got some pretty interesting applications. This idea of bounding functions is something that we're going to use a lot later, way later on in the year when we're in our infinite series unit. So when we're talking about Taylor series and we're talking about convergence and things like that, we're going to talk about comparing functions. That's sort of what we're getting into there with the squeeze theorem. Okay, so last thing that I really want to look at here, and then we'll look at a couple of applications of this limit. So we have this limit as x approaches 0 of sine x over x being equal to 1. Well, if we think about how we did the last problem, you might think, okay, I'm going to go through and I'm just going to say, I know sine x can be bounded between 1 and -1. And that would be a good place to try to start. Now, notice in order to get the function in the middle to look like what I want, I would have to divide by x. Well, there's a couple of problems with that. On the problem above, when I divided by x, or when I multiplied by x squared was always a positive number, so it wasn't going to change my inequality. If I divide by x could be positive or negative. So I'm sort of looking at the idea of I have one case if x is positive, another case if x is negative, and then a third case really if x is 0, then it's going to give me different behavior as well. So I'm already seeing that this might be a problem. But let's just assume x is positive. So I would get -1 over x is less than or equal to sine x over x is less than or equal to 1 over x. Well, think about the limits of the outside parts there. The limit of -1 over x doesn't exist. The limit of 1 over x doesn't exist. But the squeeze theorem doesn't say anything about the outside limits not existing. If those two don't exist, then the limit of the middle also doesn't exist. The squeeze theorem says if the two outside limits both exist and they're the same, then the inside limit has to be the same. So this is really a bad path that I've chosen. This is not going to work for me in this case. So we have to find a better starting point. And that's where this gets a little bit tricky on this one. So what I want to do here is I want to come up with some sort of a starting point that's going to allow me to solve this limit out. And remember, I told you want to memorize this limit. It's because you don't want to have to remember how to do this proof. And I'm going to briefly show you this proof I'm not expecting you to recreate this, but I do want you to understand the logic behind it. So as you go through this, don't try to copy this down or write it down or anything. Really, what I want you to do is just watch as I solve through this limit and try to make sure that it's making sense to you as we work through the problem here. So I didn't have a good place to start. So what I'm going to do is I'm going to think about another way that I can do this. And what I'm going to use is my unit circle. If I'm looking at the unit circle and I have some angle here, x, well, if I were on the unit circle, this would be the point 1, 0. And wherever this point is, I know the x-coordinate on the unit circle is the cosine, and I know the y-coordinate is the sine. Okay, so I need to have some sort of compound inequality that I can use for this. And I'm going to create some geometry here, some geometric shapes that are going to allow me to solve this out. So notice I drew in a secant line between the cosine x, sine x point and the point 1, 0. That is essentially this triangle. And that triangle has a base of 1, and it has a height right here of sine x. Okay, so base of 1, a height of sine x. If I took the area of that, my area would be 1/2 sine x. Now I'm going to do the same thing with that sector of the circle. So the sector of the circle, I've got basically the same kind of setup here, except this time I'm using the actual sector of the circle. Remember, for the area of a sector of a circle, I know that the radius here is 1. All I'm doing is taking the percentage of the circle times the area of the circle. So my area here would be pi r squared. So pi times 1 squared. And then the percentage of the circle, well, I know I have x radians carved out of that circle, out of the 2 pi radians that were there. And that's going to end up giving me, if you see the pi's here are going to cancel out. And in the end, I'm going to get x over 2. Okay, so now I've got 2 things I can use for comparison. And the third one I'm going to use, I'm going to go back and I'm going to extend out. I'm going to do it in a different color so you can sort of see it. I'm going to extend out that radius line that I had going up to the cosine x, sine x. And what it creates is a larger triangle. And with this larger triangle, now what I've got is a third geometric shape I can use for comparison. There's my 1, there's my x, and I'm trying to find out what this height is. Well, the height of that, if you think about what would relate those 3 things together, if I know the angle of a right triangle and I know the opposite side and I know the adjacent side, opposite and adjacent, you should be thinking about tangent. So I know here tangent x is equal to h over 1. So the height of this triangle is essentially tangent x. So this area would be 1/2, my base is 1, and my height is tangent x. Okay, so now comparing those 3 figures, I can see that I've got this setup, 1/2 sine x. That's the smallest of my areas. 1/2 x, or x over 2, is the next largest. And then the biggest one I have is 1/2 tangent x. Okay, so that's going to be our starting point for our squeeze theorem. So right now, what's in the middle doesn't look a lot like what I want it to look like, but we can do some work here to make that happen. Now, first of all, I can simplify this a little bit. I can remove this 1/2 from all of these. It's not going to change anything about my inequality. So just to simplify it, I'm going to rewrite it as sine x less than or equal to x less than or equal to tangent x. Okay, so now somehow I need to get sine x in the middle of this inequality. And I can't multiply by sine x. So really my only option is to divide everything here by sine x. So I'm going to write it in a different color just to make it really clear what's happening. Okay, so when I do that, this becomes 1 is less than or equal to x over sine x. And then that's less than or equal to, well, this is sine over cosine divided by sine. That gives me 1 over cosine x. You might be wondering what would happen if the sine of x were positive or were negative. Wouldn't that switch the inequality? First of all, it wouldn't really make a difference. But the second thing is we're working in the first quadrant here. So in the end, for this part, I can assume that this is going to be positive. Okay, so this is close to what I want it to look like. But notice what's in the middle doesn't look exactly the same as the function I'm trying to work with. I'm trying to work with the function sine x over x. I have x over sine x. So what I'd like to be able to do is take the reciprocal. So off to the side here, before I take the reciprocal, let's think about what would happen if I had, like, let's say 1 is less than 2 is less than 3. Okay, so that's an inequality I know to be true. Let's say I took the reciprocal of all of those terms. I would get 1, 1/2, 1/3. And notice now, by taking the reciprocal, I've changed the inequality to sort of be in the reverse order. So the largest number is now on the left, the smallest number is now on the right. So we're going to do that same thing here. We're going to take the reciprocal of all of these terms. 1 is greater than or equal to sine x over x, and that's greater than or equal to the cosine of x. Okay, so now that we've gotten here, we finally got to the point that we were looking for where we could use the squeeze theorem. I want the limit as x approaches 0 of 1. That would be 1. Over here on the right side, the limit as x approaches 0 of cosine x would also be 1. So thankfully, those are both the same, because if they weren't, then that wouldn't really give us any information. But since those are both the same, we can say, therefore, the limit as x approaches 0 of sine x over x is equal to 1. Okay, so in the end, that's what our limit was. Now, you can see that's quite a bit of work. Not a ton of written work, but a lot of conceptual ideas going into that. So that's not something, like I said, it's not something I'm going to ask you to do. It's not something you have to be able to recreate the proof. I'm not going to ask you about the proof, none of that stuff. You do need to understand the squeeze theorem logic, but you don't have to be able to do that. That's why I said, make sure you have this memorized, because there's not really a good way to come up with that outside of working through that proof. Okay, so a few special case problems that you're going to see on your homework and moving forward that deal with this limit are sort of variations of that type of function. So there's sort of a shortcut to this. There's a pattern to this that we can come up with. So we've got this limit as x approaches 0 of sine 2x over x. There's a couple of ways to approach this problem. What I'd like you to do is graph that and tell me what you think that that's approaching. Okay, so when you have it graphed, you should see that this is approaching a value of 2. And there's actually a pattern to this. Whatever that argument is multiplied by, whatever that x gets multiplied by in the argument, that's going to multiply your limit by that value. So if we had sine of 5x over x, that would give us 5. If we had sine of 10x over x, that would give us 10, and so on. And we could show that using trig properties. I'm not going to go through all the properties and prove that rule, but it's a general rule that we can follow. Okay, so combining that with the limit properties that we already know, now we've got a few more of these that I want you to try. And what I want you to do here is just take a couple of minutes, pause the video, see if you can solve these 3 questions. And then when you unpause it, I'll show you what the solutions are. Okay, so for this next one, you should have found that this was equal to 4/3. And the thought process for that would be the limit as x approaches 0 of sine 4x over x times 1/3 is equivalent to the limit that I started with. So now I can take the limit of this piece, that gives me 4, times 1/3, that gives me 4/3. Okay, so the next one here, this would just be equal to 5/2. And this is another one where we can use that whole idea of multiplying by 1. This is the same as the limit as x approaches 0 of sine 5x over x divided by sine 2x over x. So essentially, I've multiplied the numerator by 1 over x and the denominator by 1 over x. And then the last one, you should have found for this one that it was equal to 4. So again, we have to think about our algebraic manipulation here. We know how to deal with sine x over x. So I can rewrite this as sine of 4x over cosine 4x over x. And then if I just rewrite that, that's the same as the limit as x approaches 0 of sine 4x over x times 1 over cosine 4x. And from that, you can see that for this piece, we're going to get 4. And for this piece, cosine of 0 is 1. So we have 4 times 1, which is 4. In general, when we're dealing with the tangent of something times x over x, it's going to follow the same rule as sine of something times x over x. It's going to follow that same pattern where we can use that shortcut because that cosine is always going to give you 1 in that case. Okay, so that's everything for this section. As far as the homework goes, you'll see a lot of mixtures of different types of problems, but definitely pay attention to this particular type of problem that I just showed you here. You're definitely going to see some of those on your quiz next time. And in general, you know, what we're trying to do right now is just focus on evaluating the limits, but don't forget, how do we justify that a limit exists? Remember, the left-hand limit has to equal the right-hand limit. And then the other part is don't forget how to use that squeeze theorem.